So let's see if whatever we have learned so far in this chapter, we can actually put that to real use. And that's where the component called inductor comes in picture. So inductor basically is a device, is an electric component, and how do we use it, where do we use it, all those things we learn as we proceed. But so far, according to whatever we have learned, we have three basic devices. One is called obviously resistor, then you have your capacitor, and now we have the third important electric component called inductor. But before we get into what inductor is, let's try to learn what inductance. So inductor is the device, inductance is the amount of whatever the job of inductance is, the magnitude is called inductance, right? And I'm actually avoiding mentioning what inductor actually does. That is for later discussion, right? So yeah, let's do this. So just like resistance is the amount of opposition to flow of current, and resistor is the device, just like that inductor is the component itself, and inductance is going to be the magnitude of it, right? Anyway, let's see how does this arrive. All right, so we have already known for quite a while now that magnetic flux through any coil, magnetic flux through, and I'll in fact stop writing phi b, the subscript. It's obvious by now that definitely whenever I write phi, it's going to mean magnetic flux, not electric flux, right? So magnetic flux is in fact directly proportional to the amount of current that is induced in the other coil. This is basically, a Faraday's law, which says that EMF, which by the way is directly proportional to current, and EMF in itself is directly proportional to the changing flux, right? So, and since EMF is directly proportional to current, I can totally write this, right? So yeah, so this is pretty clear, this equation that I have written. So phi is directly proportional to current. However, if instead of one loop we had multiple loops, say n number of loops, so if we have n number of loops, then the total flux associated with that n number of loops would in fact be n times phi. And this term right here is what we call it as the flux linkage. Call it as the flux linkage, the flux associated with it. It's called flux linkage. All right, and flux linkage to any coil is directly proportional to current. In fact, it's the other way around. Anyway, and this equation, actually it's not, I can't really call it equation yet, right, because there's no equal to sign here. But to complete this equation, we're going to need a proportionality constant, and the proportionality constant in this equation, or to this dependence of each other, the proportionality constant is called inductance. Right? Inductance, depending on the situation, is either denoted by symbol of L or is denoted by symbol M. I'll talk about that in a minute. However, the proportionality constant, let's go with M for now, right? So if I write the proportionality constant and if I rewrite that equation looks like N phi is equal to M I. Alright, so N is basically number of turns, phi is the flux through each turn, so therefore the total flux would be N phi is directly proportional to M, the inductance, times the current in the coil. Alright, and now for the terms L and M. So if in fact the flux associated with the coil is a result of changing current or changing magnetic field due to the same coil, then such a inductance is called self-inductance, and we use symbol L for self-inductance. So whenever you see terms L, we are talking about self inductance. And if the changing current in one coil is leading to change of flux in the other coil, then such an inductance is called mutual inductance. Is called mutual inductance. All right, fine. So basically, that's what an inductance is. Inductance basically is a proportionality constant in this equation right here. It is a proportionality constant in this equation. However, now what does the inductance depend on? Looks like since flux phi depends on magnetic field, and I can in fact take this I to the left hand side and eventually end up writing that M is equal to N phi by I. So clearly we would have inclination to say that the inductance of a coil depends on magnetic field or area, and it also depends on current. We'll have inclination to say all those things, but in fact that's not true. The inductance of a coil and we'll discuss as we proceed why the inductance of a coil, inductance, mutual or self, doesn't really matter as far as the properties are concerned. I mean, as far as the things that the inductance depends on are concerned, inductance of a coil depends on number one, it depends in fact on number of turns. So it does in fact depend on N, number of turns that your coil has. So inductance, the inductor actually is going to look like this. This is how you represent the inductor. So inductance of a coil depends on number of turns. Second, it depends on the medium. Medium as in inductance usually being a coil. So what kind of medium that we have inside the coil? Is it just vacuum, or is there some kind of material you have filled in there, right? Based on that, and how it depends, that also is for later discussion, but it does depend on the medium between the or inside the coil. And third quantity that it depends on is the dimensions of the coil. Itself depends on dimensions of the coil itself. Dimensions like looks like it's like a cylinder. It's more like a solenoid, this inductor, right? So solenoid will have its own radius, and it will also have its own length. So by dimensions I mean radius and length. So it depends on those things and nothing else. The inductance doesn't depend on anything else. Depends on number of turns, depends on the medium inside the inductor, and depends on the dimensions of the inductor. It does not, irrespective of, it appears so that it depends on magnetic field or current or area. In fact it does depend on, but yeah, magnetic field and current, it seems to be depending on those quantities, but it does not depend on those quantities, and we'll see why as we proceed later, right? So that's the quantities on which inductance depends on. And inductor or inductance has SI unit of inductance, and this is a like electric component, right? And both the electric components that we have already learned, the capacitor and resistor, they have their own SI unit, right? So inductor's SI unit is Henry. Its SI unit is Henry. Be it mutual inductance of self or self inductance, doesn't really matter. The SI unit is going to be still Henry. And I think I did not feel that I did justice to explanation of mutual and self inductance. I'll just quickly try to explain that. Say let's say I have one coil, single coil. Alright, so let's talk about self inductance first. So I have a coil, more like a solenoid this coil is, right? So I have a coil like that. Let's say you pass some current in this coil. So let's say you are passing some current in this coil. So current enters from there and leaves from here. The same current leaves from here. If this current is constant, that's the end of it. you are never going to have any sort of induced EMF across this. If this current is constant, there is no point in discussing this. However, however, if this current is changing with respect to time, then this changing, you already know this, that I'll just be a little get a little you know let's geek out a little here and then get into math a little bit. We know that magnetic field due to a solenoid is mu naught n into I. If this current is changing with respect to time, I'm thinking magnetic field is changing with respect to time. And what's the direction of magnetic field? Don't forget that for an ideal solenoid, the magnetic field is along the axis. In fact, it's like that, the magnetic field, right? If the magnetic field is, if the current is changing, by the way, it's let's say this current is time dependent current. If the current is changing with respect to time, if the current changes with respect to time, magnetic field, which is directly proportional to the current in the coil, magnetic field is also going to change, and flux, which by the way is directly proportional to magnetic field, right? This is how you define flux, right? So flux is also going to change, and this changing flux is going to create an EMF, right? So whenever this thing happens, so you notice that changing current in this very coil led to some sort of induced EMF in the very same coil, and that's why such a phenomenon, if this thing is happening, then we call it as self-inductance. I hope that clarifies that. It's called self-inductance. It's called self-inductance when changing current in the same coil leads to changing flux in the same coil. It's called self-inductance, right? Mutual inductance, actually I have a diagram ready here, so let's look at the mutual inductance. Mutual inductance, in fact, you'll have two coils. Let's call the inner coil C1, and the outer coil, let's call that coil C2, right? So, and both these coils in fact have current through them, but let's say for the argument's sake, it's the inner coil which does not have any current and the outer coil has got current, right? So let's say outer coil has got current. We will, and since we are naming it coil C2, let's say that current is I2. So current in the outer coil. So for outer coil C2, the larger coil, let's say current is I2. Now notice, the inner coil is along the axis of the outer coil itself, right? So I'm thinking the magnetic field of outer coil would be again mu naught into whatever the number of turns that the outer coil has per unit length, N2 into I2. If I2 is a time dependent function, if I2 changes with respect to time, then magnetic field also is going to change with respect to time. If magnetic field changes with respect to time, the flux through first coil, how come magnetic field B2 is going to give flux V1? Notice this carefully, guys. You know, the magnetic field lines of the outer coil, I'll try to draw that with the green color. The green line you see right now is the magnetic field due to the yellow color coil or the outer coil, and thanks to magnetic field being along the axis of the coil C2, the coil C1 lies on its axis. I repeat this. See, actually coil C2 will produce magnetic field along its own axis. The yellow color coil will produce magnetic field, the green color magnetic field along its own axis. But the coil C1 happens to be at its axis. So whatever the magnetic field B2, which is created by second coil, is going to create flux Phi1 across the first coil. So Phi1 is actually flux through first coil. Anyway, we'll see how much that flux is and all that in a minute. But I'm here to make this argument that if current in the second coil changes, magnetic field produced by the second coil changes. And if the magnetic field produced by the second coil changes, the flux through the first coil changes. So, mutual induction is this. Mutual induction is this. When changing current in one coil leads to changing magnetic flux through the other coil. It's called mutual induction, right? And the quantities that the mutual induction or the self inductance both depend on the same thing, that number of turns and medium and dimensions, all those things are still the same. These things are still the same. However, based on how that induction was taking place, how the induction was taking place, you know categorize them as mutual inductance and self inductance. All right, let's dig in a little deeper into the mutual induction part of it. Let's try that. Let's try, right? So I'm trying to I'll in fact try to get the expression for the M term here, the mutual induction term here, right? Let's try. It's pretty simple. It'll be done in no time. So the quantities associated with coil C2, I'll be writing them here. So quantities associated with coil C2 are I2, as already mentioned, is current through coil C2. Number of turns per unit length of second coil, let it be N2. Length of the second coil, let it be L2. Magnetic field created by the second coil, let it be B2. Radius of the second coil, let it be R2. Flux through the second coil, let it be phi2. All two terms. And same thing for first coil. So for first coil, exact same things except with ones, so I1 and N1, L1 is going to be its length, B1 is going to be its magnetic field, R1 is going to be its radius, and phi1 is going to be the flux through that first coil. Alright, so let's say we have these terms, and let's try to in fact discuss through this diagram. Now that I have drawn this diagram in a in a larger way, let's try to discuss this thing right here. Let's try to get an expression for mutual inductance. We'll try to in fact get an expression for that M there, mutual inductance. Let's make an attempt. It's pretty simple, this attempt. Alright, so yeah, I'm trying to get the expression of mutual inductance, and what is going to be my governing equation here? My governing equation will still be this: the flux linkage through a coil is M times the current through that coil, right? But here the flux linkage would be due to the other coil, so the other coil is going to create the flux through this coil, right? Let's say I want to get the expression for mutual inductance of first coil due to second coil, of the first due to the second, is in fact going to be equal to number of turns in second coil into flux of second coil into I'm sorry the flux is actually changing through first coil, right? So it will be N1 times phi1 is equal to M12 times I2, right? So I'm just rewriting this expression here in the yellow box with the appropriate variables here, right? So yeah, I hope this makes sense right now. Alright, now only thing that is left out for us is to identify this thing, right? So let's do it one by one. N1 is actually total number of turns, guys. Whenever we write capital N in magnetism, that means it's a total number of turns. Total number of turns. But looks like in the variables that we have defined here, over here, the variables we have defined, we never have defined total number of turns. But in fact, there is a simple way to write N1. Total number of turns in coil C1 would be number of turns per unit length of coil C1 multiplied by length of coil C1, right? So the number of turns per unit length multiplied by its own length is actually going to give me total number of turns. So that this right here is capital N, N1, this bracket right here. Flux phi1, alright, let's try to write the expression for that. We know that magnetic flux basically is defined by as B into area into cos theta, although I really don't have to worry about cos theta here, that because it's going to be 1. Why it will be 1 is because all these bunch of blue coils that you see here in the blue loops that you see here in the coil C2 are actually in the same direction as the magnetic field. So the area and the field makes 0 degree, therefore cos 0 is 1, so I don't really have to worry about cos theta. Alright, but let's focus on B and delta S. Flux phi 1. The flux through coil 1, I'll again be using arrows to point out. The flux through this coil, guys, the flux through this coil is actually due to magnetic field produced by this coil. I'll do that again. I'll do the pointing once again. The flux through coil C1 is due to the magnetic field produced by coil C2. I hope you understand. That's why we are discussing mutual inductance. We're not discussing self-inductance in detail. We'll come back to the whole self-inductance discussion in a minute. But yeah, right now we're discussing mutual induction, right? So yeah. So the flux through flux through first coil is due to magnetic field due to first coil, right? So flux through first coil would be in fact B2. The magnetic field produced, this magnetic field is going to create flux across this coil. So it's going to be B2 times area A1. Field is created by this coil, but area is going to be its own area, right? So area is still going to be its own area, right? So B2 into A1 cos theta, like I said, we really don't have to worry about that. So B2 into A1, all right, should be equal to, I don't know, the RHS is pretty simple, M12 times I2. We will not be doing much with that. M12 into I2. Let's try to simplify this. So yeah, now I'll just rewrite the terms that I can't do anything about. So N1 I can't really do anything about that. L1 also I can't really do anything about that. I can maybe try and write an expression for B2. I'll use a different color for that. So magnetic field B2, in fact, it's again the coil C2 is once again solenoid, right? So magnetic field due to a solenoid, as you already know, is in fact mu naught into number of turns of that coil. So mu naught into N2. What's the magnetic? First of all, I'll write the expression for magnetic field here first. Due to a solenoid, magnetic field due to a solenoid is mu naught into N into I, right? So I'm trying to write that. So B2 would be mu naught into N2 into I2 times area. Area, I think we can in fact write the expression for area as pi into, what's the radius of first coil? This right here, radius of the first coil. Look at the green color. Radius of the first coil, so pi r squared. So pi into r1 squared is in fact equal to, the LHS again remains the same, M12 times I2. The 1, 2 and 2, all the numbers you see here are subscripts. I have been drawing them a little large, but yeah, they are all subscripts. Let me try to simplify this. I think the i's on both sides get cancelled, and with that I'm left with, I'll rearrange this equation and maybe in fact write it as M12. All I have left in RHS is M12, so I'll write M12 as mu naught, the remaining terms on LHS, except that I'm writing it on RHS. So mu naught N1 N2 pi R1 squared times L1, and this right here is the expression for mutual inductance of second coil due to, this is the expression for mutual inductance of first coil due to second coil. So that is M12 for you, M12. And I'll not be spending too much time on the second part, but if you proceed the exact same way as we just did, you are going to find, in fact you can try before I do it, try to write an expression for M21. What do you think that would be? That would in fact be replacing all the 1s with 2s and 2s with 1. So that expression would be mu naught N1 N2 pi R2 squared times L2, and there, that right there is your expression for mutual inductance of second coil due to first coil. So there you go, you have your expression for mutual inductance of first coil due to second coil and mutual inductance of second coil due to first coil. And let's see if this expression right here actually satisfies the terms that we said that mutual inductance or self inductance depends on. What are the quantities that the inductance we said depends on? We said that it depends on number of turns. Does it really depend on number of turns? Let's see here. Yeah, n1 into n2, that's all about number of turns. All right, what else does it we say it depends on? We said it depends on the medium. Now here we have not filled anything in this present diagram. All we had was vacuum inside, right? But if we had something, then it would actually depend on that medium. But as long as we have vacuum, it does depend on, look at that, look at the mu naught part of it. It does depend on what the medium is. So mu naught is actually, if you have some other medium, then extra term will be coming here, just like your dielectric. In electrostatics you have a similar term here, we'll talk about that later. But for now, at least mu naught suggests that it does depend on the medium. All right, what's the third thing it depends on? Dimensions of the coil. It depends on dimensions of the coil. Does it really depend on dimensions of the coil? Looks like it does, right? Look at this, the radius and length. So it does depend on dimensions of the coil. And does it now, and this by the way is the expression for mutual inductance, guys, right? And does it now seem to be depending on current? No. Does it depend on magnetic field? It looked like it would depend on magnetic field, but apparently it doesn't, right? Turns out that magnetic field term got vanished somewhere in there while we were trying to arrive at the expression for mutual inductance. Alright, so then there you go, that's the expression for mutual inductance of first coil due to second coil or second coil due to first coil, only just replacing the terms. And I hope you understood. This part in fact gets a little tricky, actually this part gets a little tricky, this part, like which how does B2 comes, and then how come this is A1, why it is B2 into A1, why not the other way around, how come like ones and twos. Listen to that portion, maybe if you've not, if there was anything misleading, please listen to that portions. I've not made any mistakes there, thankfully, while saying something. Yeah, so it's listen to that portion carefully and you will definitely understand that, and eventually you will arrive at the expression for mutual inductance. And what's the unit of mutual inductance? That is still Henry. It is still Henry with a capital H, Henry. Alright, yeah, that's about mutual inductance. However, now let's see.